Hello, welcome to the architecture of Oban. As you might notice in looking at it right up front, it's going to be a little bit different. That is, in fact, a picture of some graph paper. And what's behind it is granite from my kitchen. And the reason for this is that most of the thinking, design kind of thinking that I do tends to be done with pen and paper. And a lot of the conversations happen in our kitchen. So I happen to be in an Airstream right now, and that's not that's not the kitchen, but I think it sets a good tone. So welcome, and let's start. So I'm Parker Selbert. I go by Soren to most places on the web, GitHub, Slack, those kinds of things. I am a partner in Soren who make Oban, and that's my partner there on the left. That's Shannon. And I'm also a principal developer at DScout, where we make very extensive use of Oban. I think we have over 50 workers and counting. So we're going to start with a slightly loaded term. Architecture and design in general, I think are a bit contentious, but I think they fit pretty well for what we're going to talk about today. And so architecture in general is the structure and flow of rooms in a particular, in a building, which is kind of like a system, and that each room has its own purpose and people and things flow between them. And so in the sense we're talking about architecture today, it's the flow of data between components of a system. And this will probably not be a surprise considering that you're looking at photos of some drawings, but there's no code. So we're only going to look at processes and system state. And when I say processes, I mean both beam processes and outside processes like Postgres or some other system. We're not going to look at modules or functions. They are a little bit outside of what's important. They're kind of fluid. I can change the module names or the function names or the arity, but that doesn't change the way that the entire system is actually structured and needs to function. Those things are a bit more permanent and long lasting and harder to say remodel. And finally, if you're not familiar with Oban, this is going to be pretty important for the rest of the talk. It's a background job processor, and it's built in Elixir and on modern Postgres. And so by background job processor, we mean something that executes work that your application needs to do outside of the main. It doesn't block anything. Not so strange in the beam since no process blocks anything. But what's a little bit different, and the important bit about running it in Postgres, is that it's persistent. And that means we put something in atomically using those kind of ACID guarantees. And then we process it either on the same node or another node. And then we also have the ability to introspect on what actually happened with it. How did it run? When did it run? And that kind of information. So we're going to start with topology. And the topology is where Oban fits within the ecosystem, within its particular position in an application or within a system. And the first important part to delve into there is that Oban is a bit different than other job processors because it's a hybrid of a queue system and a stream. And so I think most people are familiar with queues as a simple first in, first out kind of thing. You push something in, you pop something out, or even priority queues where some things bubble up to the top. But where it's different and it's a bit more like a stream is an infinite bit of data, and I can look at any point in the stream, but once I look at something, it still stays in the stream at the end. And so if you look here, we can see the two little green blocks being pushed into our different streams, our parallel streams. And then we have something which is the yellow, which is reading it and then processing it, but they stay in place. And that means that they're there after they've ran, and I can look at them later. And I can see if something ran or when or how many times it failed. And eventually, since we can't have an infinite stream, we wouldn't have any storage left over, we need to clean it up. And so in a system like Kafka or something, that would be compaction. And in this case, we call it pruning, which means that we're just deleting old things that we don't need to observe anymore. And the state that things flow through the queue is really important and central to the architectural bits we're going to look at later. And so that's where the open state machine comes in. So if we look at the green blocks, we have scheduled, available, and retriable. And things have to transition between states to be usable. So I could put a job in and say, I want it to run in an hour, and that would be in the scheduled state. And it's going to move to the available state. And then once a particular system or sorry, a queue is ready to run it, it will pop it out of the available state, transition it to executing, and then do its thing with it, execute whatever code happens to be in it. They could be sending an email or processing media, whatever it happens to be. And if that works, and we don't have any errors or issues, it transitions to completed. If for some reason it errored, and we might be able to retry it again later because it was an ephemeral error, it'll go to retriable and it goes back into the queue, into the loop and can run again later. However, if there's something terminal, and there's no way it's going to work, then we can move it to discarded, or we can manually intervene and say something's been running too long, and we can cancel it, and then it goes to the canceled state. And once things are within the system itself, there is an Oban application, but it's really lightweight. And that Oban application is just a thin registry. And the registry stores configuration and the names of the various instances. And so here we're using instance to really mean a sub-supervision tree. And we have A, B, and C, and those are totally different instances that are sitting by themselves. They can run different queues, they could run different plugins, they could connect to different databases, different tables, but we can still look them all up in one central place. And all of the modules in there have the ability to look up that config, which we're going to see a little bit later, how that's sort of central to everything. And it's the core to any running instance. And then one last little bit is the way that Oban actually lives inside of an application is it's its own supervision tree, and then it also co-ops Ecto, which the rest of your application could be using to interact with Postgres. And because of that, it can use that shared pool to do things like fetching more jobs or transitioning jobs. That means it only has to have one extra connection, and it uses that for PubSub, which sounds like it might be kind of minor, but is really central to how Oban is able to communicate and scale across nodes. And so those instances are connected through Postgres. I can see that there are two tables here. We have a public table and a private table, and they're both connected through nodes. And that means that node A and node B, they can interact with the exact same data, which is not that mysterious. We work with databases all the time. But what's really important is that there's isolation about the messages that go into the public and the private. And this might seem slightly esoteric, but it's a fairly common thing to do. And in the example of the getoban.com site, there's a public demo, so you can look at what jobs are running and manipulate them. And then there's also a private backend that manages payments and emails and things like that. And so it's a very practical way to provide isolation and allow different apps, or in an umbrella kind of situation, to all live side by side and not interfere with each other at all. So going one level deep after the topology, we have the survey, and that's kind of within a particular block of land, how does something lay? How does it integrate with the surroundings? And the first bit of building something anywhere is going to actually be preparing the land. And so we can call that a migration. And Oban has a sense of a fairly unique way to do migrations in that it allows it to change over time. So there are different versions of how we're going to build things out. And in this case, if we look at the green V1, well, that set up the jobs table and it built a trigger. But that trigger wasn't quite right. So in V2, we replaced that trigger with something else. And then very crucially, we recorded what version we had migrated to in that central V9 kind of thing. And that lets us go back later, and when new code is released or we need to change something, the migration can look and see, what's the last one we had? Oh, it was V6. Okay, well now we have to do V7, V8, and V9, and it will progress through those. And we can roll back and roll forward, and that's allowed us to add uh, on top of something so that it's not fixed and you don't have to have any downtime. You can just keep running things happily for the most part, unless you have a lot of jobs, in which case it can cause trouble. But ignoring that, let's look at the table. So in the initial image, we looked at these queues and streams like they were um, side by side multiple things. But within Oban, they're actually condensed and compressed into a single table. And within that table, we can very efficiently fetch jobs for any particular queue. But because they're in one place, we can also go through. And even if you have 100 queues, we can just delete all the old completed stuff. We can prune it out without having to look at 100 different tables. And we also have very efficient indexes that are a compound, but that let us fetch jobs efficiently and um, do other things, query efficiently, count efficiently, all in one place. And then looking at those states over time, we have three sort of interaction modes. One is from your client, and that's inserting jobs. That still goes through Oban to add things like uniqueness and to insert multiple things and do validation. Then there are queues, and the queues themselves go and fetch data, execute data, manage the state of those things. And then we have plugins. And plugins, like the pruner plugin, go and modify those. And in this case, the pruner plugin deletes them based on time in a configurable kind of way. But we can have plugins of any kind, even written by individuals, and sort of like any plugin system would have. And you can move things around. Maybe things have been sitting too long and you need to change their state, and that's entirely possible. Now going one level deeper, we have the plan. So if I'm looking at a building, there's a plan for the building that's it focuses in a bit tighter and looks at the actual structure. And to build an Oban instance, we take some configuration, a bunch of options, just a keyword list of modules and names and values, and we pass it through when we start the link, normalize it, validate it, and finally persist it into this central config bit. Now, I mentioned before that the config is what's passed to plugins, and we can see on the top in the blue, the cron and the pruner and the stager. Those are plugins that are all optional, even if they are somewhat important. You don't want to run them all the time, and you might want to separately configure them to do different things. And then we also have queues. So each of those queues gets an instance of the config, and that tells them how to behave, what to connect to, and what the limit is, how many things they can run in parallel. And then we have a few, just a couple of processes of or modules that are involved in every supervision tree. So it's actually very lightweight if you don't have many plugins or queues running. And then we can look at an individual Oban instance layout. And so I mentioned it's pretty tight. If we start on the outside, there's your app that's hosting it, one or more of them. There's the registry that knows about all the things that are in that particular supervisor. And then on the left wing, we have plugins that are all optional. And then on the right wing, we have the queues. And the queues all belong to a queue supervisor. And that's a dynamic supervisor, which means that you don't necessarily have to start with any queues. They can be added dynamically at runtime, totally programmatically and flexibly. There are a few processes right in the middle, the midwife and the notifier, that run with everything. So the notifier we talked about briefly before for PubSub, that's what connects and holds that connection to Postgres, and then is in charge of passing messages through to the plugins, through the queues, starting and stopping new supervisors, that kind of thing. And then the midwife, which I think is very fun as a name, and it's in charge of starting and stopping children, which is not what real midwives do, but it was just too much fun, and I couldn't let that go. So no stopping of children in the real midwifery world. And then once an instance is started, there's telemetry integration. So telemetry is a tool that's, I think, made its way into most libraries at this point. and powers the Phoenix dashboard and a lot of other things. And it's a way to get local pub sub, like local in-process pub sub events for when things happen. And then you can react to those and hook into those. And Oban has used this from the very start. One example, well, three examples here. One is for a supervisor. When you initialize, it might be really helpful to start something up because a supervisor initialized. Remember, it's all dynamic and can be done at runtime. So you could spin up or spin down new instances whenever you want. And then plugins. Whenever a plugin does whatever the plugin does, it wraps that in a little plugin span. And so we can hook into that. And if there's some error, we can report it to something like Sentry. And then queues themselves and jobs within those queues have their own events. And we use that to fuel things like the logger. So we can see when a job started, when a job stopped. And very recently, Promex came out with an Oban plugin. So you can just have something that hooks into the telemetry and generates Prometheus data and then a Grafana dashboard. So you can see nice charts of exactly what's happening. And what's great here, and what I really love, is how extensible this is. The plugins plus telemetry mean that an outside system can both inject behavior into an Oban supervisor and observe what's happening in the Oban supervisor. And this is something that Oban Pro does. Oban Pro doesn't require swapping out a core module of Oban in any way. It just adds plugins that then do their own thing, and workers that then listen for certain jobs and embed their own metadata. And it's really been beautiful, to be totally honest. And anybody who wanted to build their own plugin system could, and wants to build something based on the metadata like Promex did, they totally can. And then we're going to go one level deeper into the most nitty gritty bit of detailed connections within things. So we refocus based on that supervisor that we looked at before, and we'll start on the outside, where the app is, where the client that's actually using Oban is, the thing that's responsible for getting jobs into the system to make it actually useful so that it does something. And the app interacts, it still uses Oban and that config to insert jobs. And this is a place where, because it's using that central config and it has other bits of stateful knowledge, it can use things like unique features. So uniqueness in Oban is at insert time. When I want to put a job in the table, because it's stream-like and it has history of whatever it had before, we can check, does this job already exist? Does something in this queue with this worker and these args, or maybe these sub-args, does that exist? And if it does exist, we just don't do anything. But if it doesn't exist, we can go ahead and insert something. And this is all very efficient through indexes. And it just slides the job in. And then we use a trigger notification or a trigger function in Postgres to broadcast that out. So again, using the pub sub feature, that's really critical to how so many of these things actually work. The trigger function sees, all right, well, we just put a job in, job 6, and job 6 is in the default queue, broadcast out to every node, however many there might be, one or more, and let them know there's something available in the default queue. The notifier then passes that information to the default queue, and the default queue can say, oh, I'm available, I've got some space here, and it can go try to fetch some jobs. And this way, it doesn't have to rely on polling, and it can run something almost instantaneously when it gets inserted into the queue. So we'll pull back and refocus slightly and look at the midwife and notifier, which are central to how so many different things work. And the midwife is responsible, or capable, I should say, of starting, stopping new queues. And this is still done through PubSub, and it all starts from the client application. So programmatically, you could start or stop a new queue. And in this case, we'll walk through starting a queue, which is a call from the app that just turns into a message that is then broadcast out. So the notifier receives that notification saying that the action is to start a queue and what the name of the queue is and a little bit of other metadata, and then hands that off to the midwife. And the midwife has a connection to the queue supervisor, and it can see, all right, oh, I wasn't running this queue. I can start this up. So I'm going to go turn that message, hand it to the queue supervisor, and voila, we're now running the new queue. In a case where that queue is already running, it will just ignore it. Or based on some scoping, we could also have it be that only the local node happens to do this. And so this is an example of how the midwife works, but other functionality, such as scaling, meaning I don't want to process, say, 5 jobs at a time. I'll go all the way to 10. That still uses the same pub sub notification and goes directly to the queues, or stopping or pausing. They all use this exact same flow. And the notifier itself is publicly documented and can be used by client applications or client modules as well. So within a job, you could subscribe to something and notify using the same infrastructure that everything else uses. And the next bit is, so far, the little queue has been just a tiny little green rectangle with very little detail to it. And of course, that's not really what it is. It's not just one process. It's actually itself a supervision tree. So each queue is a supervisor. So we have supervisor, 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 3 levels deep. And within that, we have a producer, which is the most important process. So these are going to be the gray processes that I'm talking about now. The producer, the foreman, and the watchman. So the producer is responsible for most of the logic. It is a gen server that knows how to fetch and start jobs, handle messages, do some other important nitty-gritty kind of stuff. And in this particular example, we can see that it's linked to our Postgres table, and it's pulled out 6 jobs and has started them all up. We see 5 of them are still running, and 1 of them is just completed. But when the producer pulls those out, it then starts tasks within the foreman, which is just a task supervisor, a somewhat fancier dynamic supervisor. And the foreman then monitors each of those processes. So J1 through J6 is a task wrapping a little job exec code. So it's going to take a module and just call a function on it. There's a bit more with reporting and making sure that we handle down messages and stuff, but that's pretty much all it is. And when those finish, like J6 did, it will then go self-report that it's finished. And in this case, it's not relying on the producer to report that it finished, so that we don't have any contention and bottleneck on the producer. So I can run a queue that has 100 concurrent tasks, and they can all go down. And as long as the Ecto pool can support that, you can run through thousands and thousands of jobs a second without bottlenecking on anything. But in some cases, the task might crash, or maybe there's a timeout. You can see the J2T thing. That's in the case of we want to make sure that our job only runs for, say, a second. And if it doesn't finish within a second, then we want to shut it down. And maybe there's a linked process in there or something crashes. And in that case, because the producer is monitoring all those jobs it started, it then gets a down message and it can clean up after it. And it can report, oh, there was a crash and you need to retry this. And it transitions it to a state. Again, in a way that's not blocking and still dynamically using the foreman. Have the watchman. Another fun name, and a very purpose-built little process that normally just doesn't do anything. However, and I think this is particularly exciting, it manages graceful queue shutdown. So if you're stopping a queue just programmatically, or you're restarting a node, something like that, the system will go and shut things down in reverse order. And that means each queue is going to get this down message, and the queue supervisor is then going to look at its children and start shutting them down in reverse order. And the last child in the queue is the watchman. And the watchman gets the down message and it catches it. And it says, all right, we're shutting down. Tell the producer to pause. And then the producer pauses and it stops fetching any new jobs. But that leaves jobs that are already running. And so then the watchman will go to the foreman. The foreman is aware of how many children it has, how many jobs it has going. And the watchman will ask, how many jobs do you have? And if the number is above 0, then the watchman will say, all right, I'm going to back off for a second and I'll check back. And so it cools down and then it comes back a short bit afterwards and asks the foreman again. Now, maybe a job is shut down and we're down to 2. and then it just keeps looping until eventually we get down to 0, in which case the watchman will shut itself down, and then the whole thing can keep going. All the queues do this totally separately. And there is this other side of that, which is maybe those jobs take too long. Maybe a job's going to take a minute. You only give it 15 seconds to shut down. And in that case, the watchman will relent and everything will get force shut down. And this will leave a job in a state, this yellow executing kind of state, in the database. But what's really important and what's different from, say, a Redis type system or a task system is that it's still in the database. We didn't lose the job. We might have left it in an executing state, but we can rescue it later. We can just transition it and say, we got to retry. That just happened to get shut down. Nothing really went wrong, and we can just bump it and then run it again. And finally, the last component of a supervisor, of the Oban supervision instance, is a stager plugin. And the stager plugin replaced what used to be polling in every producer. So I mentioned before that there's a scheduled to available transition. Well, a job goes in as scheduled, and it could be scheduled in a second or a minute, but something has to move that and tell the producer, all right, it's available now, you can actually run it. And it used to be that each producer polled every second to go check those. And even if that was really fast, when you got to dozens or hundreds of queues, that's a lot of traffic for nothing. So instead of doing that, the stager plugin then runs one per instance, and it itself polls once a second. And so the producers don't do anything. They just hang back and wait for messages. So the stager will go and check in the database if there's any scheduled things to move, and then finally what's available. And then it will notify, using the same pub/sub notification system, it'll notify each queue that something's available to run, and only the ones where it actually matches. So if you have, say, alpha and gamma, and only alpha has something, only the alpha queue will fetch data, and the gamma queue will ignore it. And there's one other bit here, which you'll see that there's node 1 and node 2. Well, the staging happens across all nodes because it's a central database, but that doesn't mean that we want to actually run them back to back. So, or have some sort of contention between which one's doing something with the table or require locks, meaning table level locks. So each stager will try to get an advisory lock, and the first one to get it wins, and the second one just kind of backs off and doesn't do anything. And so in this case, we ensure there's no contention, no matter how many nodes we have. Things like pruning or cron or the stager, only one of them runs. And that's much more efficient than the polling that we used to have before. And all of this is really only possible with Elixir and OTP and the Beam. And I know this because I've tried doing it in other languages, and it was really painful. It's not the same trying to implement these things in Ruby or Python or Node, which anybody who spent time with the Beam is going to say, yes, of course not. But once you go in and try to simulate a few of these features that are not just nice to haves, but pretty necessary for a real production system, it becomes obvious how painful this actually is. So in sort of review of what we looked at before, we have the process registry. The process registry means that we can start up as we want at any time and shut them down. We're never worried about naming conflicts or whether something in Open A is going to interact with Open B, and they're totally isolated and they get cleaned up just as easily as they're started, which is amazing. And we have supervision trees. Again, nothing new to anybody who's spent time with OTP, but it means that we can have these deeply nested trees, and some of them, they're just isolated. So for the notifier, if the notifier goes down, you've seen how many things are relying on pub/sub. If the notifier goes down or loses a connection, it needs to heal itself. So it has to have some sort of circuit breaker that trips and go and re-establish the connection, and then start broadcasting data again. And because of the supervisor tree, that we don't have to worry about that. There's nothing custom that has to be done there. And then dynamic supervisors. So the shutdown flow within a queue is really reliant on dynamic supervisors to be able to just track how many children are running and what those states are. but also to get proper linking and monitoring in place. And then within that, tasks. And tasks are, they're processes, but there's some really great niceties around that, like knowing which producer called them and maintaining a reference to it so that we can, if it doesn't exit cleanly, we can do something with it. And we never leave something just hanging out in the system. We always clean up after our processes. And that's much, much nicer because we're using tasks. And something that is virtually impossible in every other system are clean timeouts. Because of reductions, we can track exactly, we can just interrupt a process anywhere we want, and it will time out pretty much right when we said it is, and nothing's going to be left in a weird state. And this is impossible to do in something like Ruby or Python. You can't interrupt something that happens unless it's doing IO or something. You can't stop it, which is an amazing superpower that we have. And finally, monitors, which are kind of the glue that pulls all this together. The dynamic supervisor monitors its tasks. The task might monitor a subtask that's timed out. And then that is all linked back to a producer through a monitor. And that means that we can handle everything cleanly and we can shut down in a safe order. And really all together, it's amazing how simple it seems, just the way they compose. So thank you for listening. I am really overwhelmed in a great way by how well the community has received Oban and the level of support that I've gotten, both personally and increasingly financially with people sponsoring it. So I ask that if your business relies on Oban, please consider supporting open source development with a pro license. So in addition to supporting open source, you also get a really pretty little web dashboard that lets you see what's going on in the system, some plugins, and some workers, which are increasingly complex and tremendous fun to build. And I hope to see just more and more adoption and be able to keep doing it.
Parker, thank you so much. It's been a pleasure to walk through the architecture with you. I found it fantastic. Thank you. And we have a lot of questions, so I'm going to dive right in because we have about 6 minutes and ask that, Manuel, if you're available to unmute, can you ask your question?
Hey, Parker. Can you talk a little bit about your journey towards the current architecture? Any places that you took inspiration from, and how has Oban's architecture changed over time?
The biggest bit of influence on it, aside from Sidekick, which is what it all kind of stemmed from, is Redis streams and the ability to go back in and clean things up afterwards. So that's where a lot of the streaming bit came from. The reliance on PubSub and this alternative non-distributed Erlang way of doing things really came out of the fact that Dscout runs in Heroku, and there's no distributed Erlang in Heroku. And so you'd be surprised. I think a lot more companies actually run on Heroku in the Elixir system, in the Elixir ecosystem, than you might guess, 30% or more. So having something that's minimal that works in any environment was hugely important. And I think that impacted a lot of how the pausing and starting, all of those things happen to work. And otherwise, so much of it just evolved based on people's use cases, of it just being that something didn't scale or something was too slow, or you in particular have influenced some things. So it's been great just driving it from the community.
Great, thank you. And next we have a few questions from Zaki. Zaki, it's great to hear from you.
Hey, great presentation. It's my first time hearing about Oban, so I hope I said it right, Oban.
Yeah, it's a free country. Do whatever you want.
For now. Quick question. You sort of answered the question between RabbitMQ and Oban. Anything you want to add to that? One's a job scheduler, one's a message broker, and they do connection management differently. Oban's a lot more, has a lot of bells and whistles on retries, where RabbitMQ is just fire and, we'll see. Connection management sort of weak on that end. So is Is that a good summary?
Yeah, I think if you look at Redis or RabbitMQ or even something like Broadway or tools that are built on those things, you would still have to build in a lot of the functionality of Oban on top of them. And some of that
Yeah,
would be harder to do. So I know it's fairly common in Rabbit to maintain it like a dead letter queue, that kind of thing.
yeah,
And so those are some things you get for free relatively because of the state tracking. And for most cases, the scaling within Postgres works out fine. But you also just like within a multi, I can do business logic, insert a job,
yeah,
they all just go together. And I know I can reference something that was just inserted and it's not going to run too fast, before data's ready. And so I think a lot of it is bells and whistles, like you said, and
yeah.
not replacing infrastructure that might be used otherwise.
Yeah, and then just a quick note, you said something about database locks, right? And
Yes.
I'm just thinking about the use case in e-commerce. I think all of us have played that role. Is you got a fast-selling item, right? You got 100 users and maybe 5 items, and you probably want to use database locks, right? Just one of the ways, you want to lock up. So how does Oban, with its superpowers, how does that help? Now in this new world.
Um, well, so it's using advisory locks. I mean, in addition to whatever other locks are happening there,
Yeah,
prevent race conditions. So like for the
yeah,
unique flow, I kind of glossed over this, but if I have 2 different transactions attempting to insert the same job, it actually uses p-hash to calculate an ID based on what those are, and then grab a lock, which works across transactions, so that we don't insert 2 of the same job ever. And so that helps when you have these really quick things. You're guaranteed that if I only want to ever sell 5, I can say, I will know that there's no way 2 jobs are going to overlap at the same time and get inserted.
Does it present some overheads, or is it just you think it's doing it better than the locks? I mean, I haven't done any benchmarking or anything, but just thinking if
It
you've
does
come across.
it does add a little bit of overhead. There's so little contention. I mean, usually you get a lot of problems from lock contention.
Yes.
What older Postgres-based queues had, because they would only use a locking mechanism. But that doesn't seem to be the case from the benchmarking I've done.
Okay, awesome. And last question, are you any plans to support distributed SQL? I know Yogabyte uses the Postgres query layer, so distributed. These are sort of new SQL, right? They use both NoSQL and SQL feature sets.
I don't know. It's things like Cetus. I could see
Yeah.
making sure that there's support for that, as long as it has the base level functionality of Postgres. Then I would be interested in supporting things. It really
Okay.
comes down to what the drivers allow.
Yeah, I've already run into problems with Yogabyte. Like it doesn't do save points and rewrite Postgres all from scratch now. Thank you for answering all my questions. Thank you.
Thanks for asking.